Hello and welcome back to Little More Learning. Today we are here with data science video, and in this video we will be starting about foundational mathematics for data science. For starting with mathematics, firstly we will dive into linear algebra. So linear algebra, what do you mean by it? That it is a branch of mathematics that deals with vectors, matrices and their transformations. So it provides us the tools to solve the systems of, like we can say, linear equations or work with the data in high dimensional spaces. So basically, it is the foundational pillar of data science. So there are some key terminologies in linear algebra, like we can understand scalar as a single number. For example, if we take 3 is a scalar quantity, -5 if you take is a scalar quantity, and 0.5 if you take is also a scalar quantity. Moving on to vectors, a vector is like a list of numbers arranged in either a row or a column, or you can understand them as 1D array. So if we consider row vector, so the example of it could be v vector equals 1, 3 and 5. So this is how you can represent a row vector. And for column vector, what we need to do is like 1, 3 and 5. This is how you represent a column vector. Next comes up matrices. Matrices are like 2D arrays. If you don't know what 2D arrays are, you can just go on to our video of arrays in data structures and algorithm. You can very well understand what 2D arrays are. So here, for example, a 2D array is something like this, that has both rows and columns. Then comes tensors. You can understand tensors as multi-dimensional arrays that generalize vectors and matrices. For example, you can take a 3D array that will be used in deep learning. Next are the applications of linear algebra. The first application is data representation. How data representation is an application of linear algebra is data sets in machine learning are stored as matrices. So we need linear algebra in that. For example, a dataset with 100 rows and 10 columns is a matrix of 100 cross 10. Then we have dimensionality reduction. It is used in principal component analysis, or we can say PCA, to reduce the number of features while preserving a variance. Then we have applications in neural network, transformation, and solving system of equations. Now, the very first step in linear algebra that we are going to take is about vectors. So, what are vectors? Vectors you can understand as a quantity that has both magnitude and direction. You might be familiar with vectors in physics that are represented something like this with an arrow above or by bold letter. So, in data science, vectors often represent features of data points or coefficients of a model. Now, there are two ways of representing a vector, that is geometric representation and algebraic representation. So, when we think about geometric representation, it is in a 3D or a 2D space. Vectors are represented as arrows pointing from one point to another. So, if we take an example of a vector, let's say it is 2, 3 and it starts at origin. So origin is 0, 0 and ends at 2, 3. So you have both the points of start to end, and you can plot a graph and it would something look like this. So this is how a vector is represented geometrically. Let's come to algebraic representation. A vector is written as a list of components in a column or a row form. So algebraically, you can write it in as a column vector or a row vector, as we just learned few moments back. So there are different kinds of vector. Firstly comes up zero vector, a vector with all components equal to 0. And for example, if we take it, zero vector is something like this. Then comes up unit vector. A vector with magnitude of 1 is called as a unit vector, and we can represent it as like this. And this is your magnitude, and for becoming a unit vector, it should be equal to 1. This is the condition. Equal vectors are those where corresponding components are identical. Suppose we have a vector v1 and its components are 1 and 2, and similarly we have a vector v2 and its components are also 1 and 2. So these two are equal vectors because their corresponding elements are equal. Opposite vectors are vectors with same magnitude but opposite direction. So now let's take up another example. If we have vectors something like this and another vector like this. So these are opposite vectors because the components are same but the direction is different. Now let's move on to some vector operations. So the first operation we can perform on any two vectors or more than that is addition. Addition is performed by adding corresponding components of two vectors. Suppose we are having two vectors v1 and v2 and these are their corresponding elements. These are column vectors, and we have, for adding these two vectors, we will add the corresponding elements, that is x1 plus x2, and for the next we will add y1 plus y2. If we take an example of a row vector here, let us take this particular example to understand more. So, we will adding, what we will be doing, we will be adding corresponding element. 2 plus 1 will become 3 and 3 plus minus 4. It is a pretty basic calculation, but still I will show. So, it becomes like this and the output will be minus 1. Subtraction. Subtraction happens in the similar way as addition is performed. And here also let's take an example. Let's say we have two vectors and we want to subtract these. What we will be doing? Subtracting corresponding elements. So here 5 minus 3 will be 2 and 7 minus 2 will be 5. So this will be our example. Then simply we have scalar multiplication, and better you will understand with an example. Scalar is in constant quantity. Suppose we have 3 and our vector is 2 comma minus 1. So the output will be 6 comma minus 3. Next come up dot products of vectors. So the dot product of two vectors measures their similarity. It is defined as v1 vector dot v2 vectors equals x1 x2 plus y1 y2. So when we consider its geometric interpretation, the dot product relates to the angle theta between the two vectors. So for geometric, if we take it geometrically, v1 vector dot v2 vectors give magnitude of v1 multiplied by magnitude of v2 and cos theta, that theta is the angle between these two vectors. And if we take a common example, let's say we have a v1 vectors that is 3, 4 and v2 vector that is 1, 2. The dot product of them, that is v1 vector dot v2 vector, will be multiplying the corresponding elements, that is x1 and x2. Here 3 and 1. So it gives us 3 and plus y1 into y2, that is 4 into 2, that is 8. So our output will be 11 for these two vectors. Then we have norm of a vector, or we can say magnitude of a vector. That is, the magnitude of a vector v is computed using the Euclidean norm or Euclidean formula, where magnitude of vector v is equal to the square of each of its components under square root. So let's take an example for this. Suppose we have a vector named v and the components are 3 and 4. So the magnitude of this vector will be square of 3 plus square of 4. So the output will be 9 plus 16, which is equals to 25 and which is equal to 5. So 5 is the magnitude of the vector v, which has the components 3 and 4. Next we have vector projection. The projection of vector v1 onto v2 is a way of expressing v1 in the direction of v2. And this is useful in data science for decomposing vectors into meaningful components. So the formula for projection of V1 onto V2 gives us dot product of V1 and V2, square of the magnitude of the V2 vector multiplied V2 vector. Let us take an example here. Suppose we have a vector V1 with components 4 and 3 and a vector V2 with components 1 and 0. Now, V1 dot V2. We will have to perform dot product, which will be 4 and 1 plus 3 and 0. So it will be equal to 4. And then we need to calculate the magnitude of our V2 vector, which will be 1 only. After you will substitute into Euclidean formula, you will obtain 1. And finally, when we are talking about projection of V2 on V1 vector, we will get 4 by 1 and this is 1, 0. So this becomes a scalar quantity, and as we know about scalar multiplication, so our projection will be 4, 0. So next comes up applications of vectors in data science, and this will be the last topic for this video. Firstly, it has application in feature representation. What it means that features in data sets are represented as vectors. Similarity measurement, and that can be calculating using the dot product of the vector. Dimensionality reduction, as we studied earlier, PCA uses it. It relies on vector projections. Then we have gradients, descent in optimization, and gradients are vectors pointing in the direction of the steepest ascent. The negative is used in optimization to find the minima. And lastly, in computer graphics and transformations, how it is used, like you can scale or rotate the graphic based on the vectors. So that's all for this video, and don't forget to like the video and subscribe to the channel. Share your valuable thoughts in the comment section. And we are also having our website live now. Do check it out for notes of various tutorials and videos. And don't forget to follow us on all the social media platforms along with YouTube. And thank you for watching this video. See you in the next video. Till then, happy learning.